Okay. Thanks so much, everybody, for attending today. Is it okay for me to start?
Yep, sure. Go ahead. Share your screen. I've introduced you.
Okay, great.
So,
wow, there's a lot of folks here today.
yep.
That's awesome. Okay, so let's get this show started here.
Share screen should be down at the bottom of the green button.
Yeah, I'm trying to make sure I can still see something while I'm talking here. Share screen, PowerPoint, that's right.
You may have to open your PowerPoint first and put it in display mode before you share screen.
Can you see it?
Yep, looks good.
Okay. All right. So thank you so much, folks, for coming tonight on today's what, Tuesday night here. I appreciate you. This is a talk that's going to focus on some of the what I think some of the most important components of hyperspectral data analysis, or at least identification. And we're going to touch on some of the concepts of acquisition, what spectra looks like, what it looks like, and what the applications can be for this in our industry. I don't have the ability to bring up all of my computational utilities, and one of the reasons why is that part of my project is being used for a NASA tech and part of a NASA tech review, and I can't say too much more than that, but we're not allowed to divulge too much. So I have to keep it at a very general scope. And but I am definitely going to take as many questions as I can. And of course, if I don't know, I'll do my best to deliver it for you at a later time. So starting out here, once again, my name is Troy Bernier. I'm with a company called H2O Resource. H2O Resource focuses on it started out focusing on water resources with the name H2O Resource, but we become very much entrenched into the data analytics world. My background is in geology as a geologist, mineralogy, water resources, GIS, very heavy on the GIS side, and that got me involved into more geospatial work. And from there, I started taking courses in hyperspectral imaging, and I never knew I would use it. But with time and my data analytics skill, it kind of became a path of some opportunities. And I will share some of those with you today. But what happened to me just a couple of years ago, during the pandemic, I got involved with a NASA team, sort of like they call it the NSPEARS, I think it's pronounced. But basically, these are people who I don't work directly for NASA, but I look at projects and help with a lot of the discussion that goes on with them. And I had some image processing skills, and the conversation came up to lunar geology. I was very excited about it, and on my fingertips were lots of data and tools, and I started getting myself involved in it, and was involved in the let's just say the potential of minerals that could exist on the moon, and that's with the lunar geology, and that's kind of like where all of this really has stemmed from. And I'm still working on it. And I'll talk a little bit more about it going forward. So next slide. Can I just hit spacebar? So hyperspectral technology is something that we all know. It's been around for quite a while, for decades, actually. And it has become cheaper, faster, and it's led to a huge amount of technical advances in statistical data analysis, applications of artificial intelligence. So this is where we're able to filter out data, take the noise out of data, really bring it down to something that could be quite useful. And these artificial intelligence new applications or algorithms allow us to classify information that's collected. And these improvements have been recognized by the increasing number of satellite deployments and image coverages that have been produced. And this slide here is just an example of just 10, 15 years of data collection from very basic multispectral, just let's say RGB into multispectral, which is 4 or 5 more bands or a few more, into ending up with Earth Observer 1, which is a hyperspectral platform. Starting with Landsat 8, which was more of the newer platforms, a big change took place. That big change took place, whereas the methodology of acquisition has changed. In the past, it was something called like a whisk broom technology, where today we now use a push broom sensor technology. And just to give you an example of this, a whisk broom technology. Can you see that?
Don't know what it's supposed to look like.
Can you see the satellite?
Looks like cloth, just cloth.
I don't think so.
It's blank screen, kind of dark.
Oh, okay. Hold on 1 second. Hold on.
Ah,
1 second. Yeah. All this technological stuff here. Hold on. Okay, more windows than I know what to do here. Hold on.
I think if it's really critical, just skip by, unless it's really critical, to skip by it, Troy.
Yeah, I will. It doesn't appear I can share it. Hold on. I'll just wing it. Okay, hold on.
Okay.
So initially, you should be able to see this. So initially, this is a satellite here, and the older type of satellites that were shown. And this satellite, the way it operates, it's a whisk broom sensor, So it's about to show you something really quick here. I'll pause it when it gets to that stage. But as the satellite passes over the surface, notice these little squares. Can everybody see these squares?
Yep.
So what happens is, as it's collecting, it's taking these little tiny snapshots and it's swishing back and forth. And, of course, we're talking a very long period of time of application development. It allowed for rapid collection. It worked really well. But the one main issue of this methodology is that it'll break. So, and that's what happened to Landsat 7. Landsat 7, if you looked at any of the data, the Landsat 7 data, you can't use it. It has all of these lines in it. It's unusable. And I don't know why it's still the data streams are still out there. But this technology here that you were looking at, this is the other satellite, Landsat 8, and going forward, it uses a push broom technology. So notice here, look at these lines. Look how this collects. So it collects entire strips at a time instead of these checkerboards. And that by itself is a significant step forward for the technology. Hold on here. So I just wanted to share that because it's important to understand why these systems are working, and if you're trying to capture data, you could have problems, and you'll be able to recognize some of those problems. But one major disadvantage that all of these systems have, and as we collect more and more data, the major disadvantage is that you end up with these extremely large data sets. I'm talking very large data sets where if you're just trying to map a county, a county within a state, you would be collecting hundreds of terabytes of data. Therefore, as the improvements in hyperspectral resolution, where today we're enjoying 30 meters pixel size, but when you look at some of the commercial platforms or some of the new platforms like with Planet Labs, they have a much smaller resolution, or even the drone systems or aircraft systems, which we're about to look at, those systems have even much smaller resolution. So your data sets can be tremendous. So of course, ideally, to improve storage requirements, price increases, but the performance goes up as well with that. To look also back at these comparisons, the Landsat bands are these strips here, whereas in hyperspectral, such as the Hyperion satellite, the EO1, it's a continuous spectra. So you don't end up with just jots of information. You end up with a long curve that represents the whole wavelength. And the one below really puts it into a much better perspective. So the Aster, Landsat, large MODIS platform, then you have the Hyperion, which is EO1. You can see the comparison here where those are these large areas, but you have these gaps in the data set, in the spectra that could be collected. Whereas in the hyperspectral, look at all of these are bands. You have up to hundreds. You could have a couple hundred bands of information that's very, very fine and very, very close together, which allows you to capture the entire spectrum, that entire curve that represents the physical structure of that material. Okay, understand the physical structure of the material and the chemical structure of the material. That's the benefit. That is the true benefit of what comes out of hyperspectral imaging. And of course, this technology, which was initially developed for mining and geology, right? Mining and geology were the initial applications for this, back in the 90s and early 2000s. But now due to those advances and reduction in size of equipment, cost, we now have this in agriculture, waste sorting and recycling, eye care. If you ever been to the eye doctor recently, they have these methods where they can they can actually tell how healthy your eye is based on the hyperspectral imagery that they collect. Food processing, another big pot is in surveillance. If you have a clearance and you're a geoscientist, you are extremely used. You can be used because you can look at landforms, geomorphology, changes and shapes, things like that, that the average person may not be trained to look at, but a geoscientist has the skill set, the skills, the knowledge, skills, and abilities to take surveillance to a much more advanced level. And this accelerated during the US time, our time in Afghanistan, because where we were also doing lots of exploration for geology, all the minerals that are in Afghanistan, we were also utilizing that same technology in surveillance. And that's how we caught, that's what helped us catch Osama bin Laden, as well as the latest guy that they literally, whatever. But so in addition, there's astronomy. We're now able to use hyperspectral data in astronomy, and a lot of especially what's coming out of the James Webb Telescope, we're seeing things that have never been imaged before, and we're now able to really push the theories beyond our imaginations.
Wow.
The other thing I want to mention, which also our industry can get involved in, is an environmental monitoring. Okay, because we're looking at water quality, watersheds, ore body waste sites. We're able to look at these with incredible detail and be able to identify the waste products themselves and the concentrations of them. biomedical imaging, and more. It's never ending. It's just an explosion of ideas with the application of hyperspectral imaging. And the best part of it all is you could do it from home. You don't have to go into the office. You can do it all from home. You don't need a large computer because everything can be put in the cloud and managed and run from there, allowing you some level of security in the comfort of your home. What does one of these platforms look like? This is the Hyperion Imaging Spectrometer, EEO1. You can see the system here. This thing weighs, I want to say it weighs probably 1,000 to 2,000 pounds, and it orbits the Earth every 16 days and collects an incredible amount of information. Not a very, very high spectral resolution. This one here is at 30 meters, I should say, because the newer platforms, commercial platforms, which you have to pay for, this is something that's given away for free for us through our tax dollars. Whereas the commercial platforms that are out there are providing 10 meter, 1 meter, and I don't even know how small. I haven't looked at some of them in the past year or so, but extremely small where you can see the person in the street, what they're doing. Last thing here is the type of equipment. Because of the size of these instruments, they're able to go into the smallest of planes, in drones. You can see the types of cameras. Do also understand that these cameras can be very expensive. A typical camera is going to set you back five figures easily, $20,000, $50,000 for a camera. Something very high grade is going to cost even more than that. They have the ability. This one here on the right is oceanography application. So also still within our industry, where this one I think is looking at coral reefs, and you're able to, we're talking about a coral reef, which with a hyperspectral imagery, you're now able to look at the health of the coral reef in ways and details that we've never been able to look at before, other than being in the ocean, taking the coral reef and having it analyzed. This is having it analyzed in situ, on site. That can be done if the data is being streamed to a platform, a notebook or something like that, where they can analyze the data on the fly. So just as we're able to analyze vegetation, health, in agriculture, we're able to look at coral reefs and other biodiverse environments. It's very exciting. And one of the most important parts, which is where I'm going to probably talk most in this, is that, okay, great. It's wonderful that we're able to capture all of this awesome information, but how do we know what's true? How do we know what's factual? How do we know what we're looking at? Well, we know what we're looking at because scientists, field personnel, field technicians go out into these environments, another part of our domain, and take hyperspectral cameras and point them at known material. So if you want to identify some particular ore body, you first need to know what it looks like in a hyperspectral image. So you go out in the field in certain environments where you know it exists, and you have your hyperspectral cameras image these products in controlled settings. And this is the field, and that is a relatively good controlled setting because the sun, do you see any shadows around this person? Anybody see any shadows? The shadows are underneath, meaning the sun is way up above him. Ideal ground field conditions. So satellites, drones, or aircraft, this reference material that they're collecting is in an ideal condition for that field environment. But even though that is the case, guess what can happen? Here are two spectra, okay? These are two spectra from the mineral monazite, right? This is a rare earth element. This is very, very important, a very important mineral, okay? Very important mineral because it contains rare earth elements, and it is critical to numerous high-tech applications, not just in the United States, but in the world. It's one of the biggest things going right now Is who's collecting the rees, who's in control of the rees, because that dominates in price, that affects so many other factors, so many geopolitical factors. So here's another area that our industry plays a significant role in. Now, what I'm showing you here is this mineral collected. This is a spectra that was collected in California. Okay, this sample came from a rock specimen in California. This specimen came from Eveland, Norway. It's the same mineral, right? It's the same mineral. But what happens to the spectra? Folks, you can definitely comment on this. The spectra look
Amplitudes are
different.
different.
The spectra is different. It's pretty. It's significantly different. However, you can
Watch the
see.
scale.
Say it again, please.
Watch the scales. The scales are different too.
Yeah, the scales are different. The amplitudes are different, right?
Yeah.
The reflectance. This is reflectance, and this is wavelength. So the reflectance here on this specimen in California has a higher reflectance than the one over here. Okay, the one on the right. And now, unless you're one of those geologists that says, "Oh, I've been to the one in California, I'm familiar with that, and I'm familiar with the one in Norway," which we do have geologists that have that level of should I say, we do have those CPGs that do have that level of experience, right?
I've worked with granites that have monazite is 1% over miles and miles and miles.
Yes, and yes, and the hyperspectral camera will be able to isolate. It will see the monazite. It will see it there, and I will prove it to you that it has the ability to see these things. But I don't know. Oh yeah, here we go. Next slide. We're looking at the same specimens, but we've got some data description here. So let's try to see if there's a difference. We still have California on the left. We have Norway on the right. Eveland, Norway on the right. So the chemical formulas are the same. Of course, we have those different locations. It's so nice to even tell us who the person was that or company that sent it in. But look at the sample description. A fine brown powder. Large single mottled reddish brown crystal.
Yeah.
See the differences? See the differences?
Can
Okay.
Can you flip back to the?
Absolutely.
Okay, so you're getting a better amplitude spectrum out of the crystal, right? Getting higher amplitude.
No, the crystal's on the right.
That's what I say, but you're getting
Yeah, the
higher.
brown powder's on the left.
Okay.
Yeah, the powder's on the left. Powder's giving us a better spectral response. However, you can see some similarities. Okay, and I'll tell you what I see. The similarities that I see this pattern is replicated. I see this pattern is very similar. These wavelets here, very similar.
Yep.
Of course, this has a more pronounced curves here, but there's still the same type of pattern here. We still have the same dip. We still have these same little bumps.
Yep.
Right? Still have the same little bumps. Okay. So for me, it's a little off, but but you have to know the area that you're in. And the good thing is, not only did we have advancements in the technologies, but the most important part was our spectral libraries have significantly improved. In the past, when I started doing these types of analyses, I ended up looking at individual professors that had their own libraries of spectral libraries, which are these. These are nothing more. I wish I had one to show you exactly what it looks like, but it's nothing more but a CSV file of points.
Yeah.
That you would have on any kind of log, geophysical log, which is it's a series of comma delimited points in one column. Same thing here, which is fed into the software to provide the software with a known signature, and then using that to look at the field data, the field image, your hyperspectral image, and it will help identify them. And we'll look at that a little later. Here's
Troy,
another one.
historically, was a fellow named Crosta responsible for some of the early patterns?
Say that one more time.
Crosta, he was an Englishman. And we used his Landsat, seven bands of information Landsat in Yemen, of all places, for 7 months to prospect for gold.
There you go. Yeah. And of course, you know, all of this was initially done on the platforms of the early Landsat platforms.
Yeah.
They didn't have the same spectral resolution, but when you're looking at somewhere like Yemen, you know, I don't know exactly what it looks like, but they could be some large areas. They could be some large areas that make it easy to observe, because it could be a large wasteland type environment.
Yeah, we had 40,000 hectares.
There you go. Okay, and you know, not to say how much relief was there, but when you're in those types of environments, when you're dealing with a spectral resolution that might be 150 meters per pixel, that will work, opposed to trying to look at something in a much smaller environment or a smaller survey where you're not going to have that control available.
We ID'd 342 Crosta anomalies, and walked up and down to them. By 324 of them, we actually got to.
Wow.
That was pretty impressive.
Wow. Awesome.
What a great, and that was 1996.
Yeah. Awesome.
I'd like to do that again with this stuff.
Yeah. Well, and it has to be done. It has to be done. Because now, you know, even though these satellites that I'm sharing with you today, they're great for this kind of work, but it's typically a mining company is going to subcontract, you know, they'll do this for their base survey, but when it comes time to really honing down and being able to do a better analysis, which will help you with a spatial analysis of what's on the surface area, you want that 1 meter resolution or
It's called
better.
boots on the ground.
Yes, it's like boots on the ground, as well as you're going to have field personnel, which will help reduce the size of your survey, which reduces the amount of money that is spent. Okay, so you know the work that was mentioned earlier, how I was in West Africa. In particular, I was in a site, Guinea-Bissau, most recently, where we helped reduce the size of the survey. It was, I don't know, 3,000 square miles initially. We reduced it to under 300 square miles because we used a geochemical prospecting tool that was running on utilizing radiometrics.
Right.
And so it was a multi-stage survey, and that particular part of the survey was able to reduce the size that needed to be studied. And that's, you know, in exploration, that's the biggest, one of the biggest components is putting in all of these surveys. And we're going to start seeing, we're definitely going to see a lot more of this, I think, in the future as people are utilizing, you know, areas in the United States and North America for surveying reeds, because they're here. They're here. We just have not been able to quantify them as the way we would like to quantify them yet because of price. So the last thing here is this is an interesting mineral here. And this is a very different spectra. And can anybody tell me why these spectra are so different from each other?
Well, one might be the crystal and one might be the powder, like the last one.
It's easier than
Well, you've got monazite and xenotime in one, and just
there you go.
Okay.
Right. You have minerals that are somewhat close to each other and the spectral signature.
Yeah.
So the interesting thing is you got them there together like that. And it shows you where you can have a similar pattern. You can have a similar pattern, right? You see this pattern here, this pattern, but it's somewhat accentuated, it's somewhat extended and distorted due to the other one that's part of the blend. So and actually both, you know, having both of these is better than just having one, I guess, unless, you know, you talk to somebody that's the process. these things physically. Excuse me. So any questions before we move on to another topic?
Yeah, in the field, do you use, then you can use drones instead of geologists to go out and check out the anomalies.
Well, yeah, the drones will conduct the mapping,
Yeah,
and then do realize the geologist can also be the one to flying the drone.
absolutely.
Okay, so get that FAA license, get yourself trained, because you could be the geologist. Either if you're not flying the drone, you may be there on site because someone who's probably going to want to also go and field check those particular areas as well. So,
Well, it really helped to have all the goats and the sheep every morning go up the hill and eat all the green stuff off the rocks. That's the problem with that part of the world. It's the green things are eaten up right away, and
right.
but it makes for great outcrops.
That's awesome.
I have a quick question, and
Sure.
I don't know if this is pertinent at this point or not, but do these images and these results, are they able to take into consideration any kind of, say, I don't know, oxidation or a dilution? Like you go from a brown powder, from the monzonite to the crystal itself. So how do you, or can you, I guess, be able to interpret that, hey, this has got some sort of oxidation happening, and this is at alteration, or is that not something that can be done?
That's a fantastic question. And in my opinion, you would see those differences. You would see.
Okay, great.
So the spectral signature is going to be somewhat different. Just the mere fact that we have some different chemical species involved here, you see how the signature is different. Just how we've seen the same mineral specimen here, but it has different properties, different physical properties.
Yeah.
One's in a powder form, the other one is a crystal. And that by itself shows it. So definitely when it comes to weathering, you're going to see that. And one of the nice things is that the company that surveys this on a regular basis, they're going to have those spectral libraries to talk about it.
Yeah.
Which will add value, to the overall project.
Yeah, so like the formula, obviously on both of these slides is the exact same. So I guess probably that was the reason for asking that question. But no, that's a great answer. Thank you very much.
Yeah, Michelle, the monazite is one of the first minerals to release its trace elements in the Sierra weathering pattern in California. And monazite has a lot of uranium, and the uranium, as well as other trace elements, goes right into the soil waters, the carbonaceous soil waters, and gets fixed in marshes and meadows.
Yes, and my experience with it, I did my undergraduate in New York City, and one of my professors, who was a geochemist, took us out on the North Shore of Long Island and the South Shore of Long Island. Actually, it was the North Shore of Long Island, where we collected rock specimens, busted up the boulders on the beach, collected rock specimens and sands, and separated it all down into the monzonite to extract those radioactive minerals. Yeah. And so, yeah, it's the nice thing about this, what you mentioned, is that washout that you would see, that washout, the weathering that produces the washout from this, you'd be able to see those natural tailings in the hyperspectral imagery.
It goes right down the creeks and into the marshes.
Yes, you would. This would be identifiable.
I've got a question.
Yes.
Okay, I'm a geologist out here in West Texas. I'm working on a large rare earth project. My question is very basic. I am looking at the eroded material coming off of rhyolite, coming off of pegmatites. Yeah. My question is very basic. At the end of this, could you supply me with a few of the companies that would be able to supply commercial data? because it's been kind of a hunt for me. I've not been able to really locate the companies that could supply hyperspectral data for what I'm doing. I've got probably close to a 10,000 acre project, and I'm going to have to shop around for what company would have the data in my area for commercial use.
Sure, absolutely. Make sure that he gets my email. Here's my email address. I'll put it in the chat.
Thank you, sir.
And I'd love to go out there and work with you. I am available.
Okay. Thank you, Troy. I'm
Yeah.
writing it down. Okay.
Yeah, I'm definitely definitely on the marketplace, guys.
Can you put that up again, sir?
It's in the chat.
Oh, it's in the chat. Okay, thank you.
Yeah,
Sorry.
I put my email address in the chat.
Thank you, sir.
So you shoot me an email and I'll be happy to point you in the right direction.
I appreciate that, Troy. Thank you very much.
You're welcome.
I think if we get too many more questions, we're not going to get to how you actually distinguish these minerals in hyperspectral data. How you process the data.
I will show you. Okay.
Yep,
Let's move forward. So when so now we're moving to the reason that I got into hyperspectral. And I was participating with a project. I was kind of recruited by a company called Azimuth Energy. They've got some GIS folks there, and as well as another team member from Kent State. And what happened was that they wanted to know, are there any minerals on the moon? Okay, what minerals are on the moon? What particular minerals are on the moon? Of course, there are minerals on the moon, but what minerals should be there? And there's this big, there's a lot of hype, a lot of interest to go to the south pole of the moon for various reasons. So after going through a pretty strong literature review, I got my hands on data sets from the Moon Mineralogy Mapper. It's the MMM or M3. Okay, it's been going around the moon for quite some time and collecting multispectral imagery from the moon.
Oh, wow.
Hyperspectral imagery. So I take this and I used a program at the time called Envy. And I ran it through the Envy system. And what it provided me was a plethora of spectra. All of these are individual minerals. All of these are individual minerals. And, which was extremely exciting for me to be on this team, where we were talking about, well, what is available on the surface of the moon that would make it feasible for a permanent lunar base?
Wow.
Okay, so there's a lot of talk right now about establishing bases on the moon. There's a lot of talk about building stuff on the moon and just putting it in low Earth orbit. I'm sorry, in lunar orbit, or somewhere in the Lagrangian orbits where they could send it off to the other planets and do all kinds of exploration. You probably also know there are a lot of people who've started companies that want to go and grab asteroids and tug them into closer to the Earth and mine them for their extremely valuable minerals that are on them. So there are numerous mineral species have been validated on the moon with hyperspectral. Moon surface rocks are made up mainly of anorthite, which is found in mafic igneous rocks. It's dark igneous rocks. It's a plagioclase feldspar. It has about 20% of aluminum and will be the main ore for aluminum and calcium on the moon. And there are many, many other minerals. There's a question?
It's asking who you are.
Okay. So going forward, I looked at the spectra here. This is for anorthite. And in this spectra here, what you have is a comparison of different samples along with the base spectrum. And, it's a high chemical variability between albite and anorthite. lunar plagioclase has less sodium compared to terrestrial plagioclase. So there's something that has to be said in the context of formation. And in this here, this is a hyperspectral image of that portion of the southern hemisphere of the moon, where we have some greens, we have some reds that resemble the mineral concentration. In this case, this reddish here, this reddish represents the albite signature. The albite signature. And for folks to know that I used programs called ENVI and ERDAS. I use these programs called ENVI and ERDAS. Really great. They're commercial platforms that make it very easy to capture and analyze the data. Do realize that there are other platforms, okay? QGIS, Python, etc. Very good programs for hyperspectral imaging. MATLAB, I use MATLAB a lot for this. And someone made a statement that the USGS maintains a library of mineral spectral signatures, and that's absolutely right. The USGS is the largest repository of spectral images. It has grown very nicely these past couple of years. They've redone the website. I was on there this week. I was able to look at quite a few things. It's very, very good. And if there's more time, I could show you how to get to that. Augite, okay, mineral identification. Possibly the colors that we see here, green, these green colors. What you'll see here is a spectra of the reference spectra, and then the field spectra. So the blue, I think the blue here is our reference spectra, and the red is the field spectra, what came out of the mineral, the M3 satellite going around the moon.
No.
So there you could see the identification of what we have on Earth, what was measured on Earth, versus what was measured from a satellite orbiting the moon.
Wow.
It exists.
And
That's pretty close, actually.
Yeah, it's very close. Okay, and this is what I was talking about, how in certain environments, and I think it was mentioned earlier, you didn't tell me your name, but someone said earlier about regarding weathering. Now, is there a lot of weathering on the moon?
Yes. Solar radiation.
the micrometeors.
Is it more than what we have on the Earth?
It's slow.
Right, right. It's nothing like what we have on the Earth. So the exposed minerals, those materials that are exposed on the surface of the moon are probably far more, let's say, clean and fresh than what would happen if we were on Earth, because of the oxidation and other weathering factors that are at play. Right. So it closely it's expected to closely match the reference signatures that we have on these minerals. Let's take a look at another one. Diopside, as represented here in these blue and green pigments, ortho-clinopyroxene mixtures. We're missing, man, the reference spectra is missing there. Anyway, but in this case, the mineral diopside is on the moon. Hematite. Hematite. Okay. This one here, you could see the reference spectra. It's a little different. It's a little different, but you know as well as I do, if we get hematite in some other part of the country, I'm sorry, of the world, there might be, I can almost guarantee there's more than one reference spectra for hematite, because hematite occurs in so many different places on Earth. And we might find one that closely fits. At the time when I did this, there weren't that many spectra available. I could probably tell you exactly where I got this one from if I go back into my library. But it does have some similarities, and it fits with what we have here. Any questions so far?
Yeah, when you're using ENVI, Troy, are you mainly looking at the depths of the troughs of the absorption features, or are you actually convolving the spectra of different minerals together to try and match the spectrum that you're looking at?
You have to, when you're looking at these spectra, it's called, it's called let me see if I have it here. But it's a type of continuum that you have to perform for it to match up to your existing spectrum. In other words, to compare it, in order to compare it. So it's sort of like you're formatting your field spectra so that it is able to be compared to your reference spectra.
Okay.
Those are the steps. And the system that, and the ENVI system, it does this with just the push of a click. Whereas, of course, with Python, you'd have to code it out, which is not that big of a deal because a lot of these codes are probably available. MATLAB, same thing. You just have to modify it based on the species that you are evaluating at the time. Like these tools, the processing tools are available in open source as well as on the commercial landscape to be able to perform a what I would call a classification, which is what I would have liked to have shown you today. A classification. I could show you what a classification looks like. But what it does, it'll take the known spectra that you have, compare it to your field spectra, and then you perform a either supervised or unsupervised classification, which then highlights all of them, isolates all of them in your coverage, in your imagery. That's how that's performed. And when you're able to do that in a geospatial environment, you're now able to, from an aerial perspective, you're able to quantify the surface area. The surface area of that mineral.
Okay,
And then start to establish some sort of, if you're able to do some sort of field survey, now you're able to take those numbers and quantify concentrations after performing some assays or so forth. You're able to do a lot more with that. So it's an excellent tool to help one identify and quantify what's on the surface.
so from a workflow perspective, you load in, like if you're looking for a certain thing, you load these spectra from like the USGS library into a data set, and then you have your field collection data. I mean, it could be from space or what, or all the way to the ground, and
Your
the
imagery file.
sort and look for the similar pattern. Is that, it's kind of like
Yes.
a
Yes.
comparison?
Yes. And so you would have your imagery file. Okay, it's an imagery file, which is it's sort of like a three-dimensional block of all those bands, hundreds of bands. You're isolating what bands you want to utilize, okay? Because you're not going to be utilizing all those bands, so you're going to find which bands fit the particular minerals that you're looking for. So you could have a suite of bands that correspond to your monetized minerals, your minerals of interest.
Yeah.
Right.
But
Okay.
and that could be the target mineral, or the target mineral can be the associated minerals.
Right.
Okay, it could be associated minerals that you're really looking for, because within those associated minerals, it's going to have the Res or the minerals of interest, monetary interest.
Got it.
Okay?
Thank you.
Different ways. So there are different ways of approaching this. And of course, remember, based on the spectral resolution, you may not be able to get to the ones that are low concentrations if you're using something like a Landsat, or you don't have the spectral resolution that's small enough for that particular ore body that you're looking for. So it depends on the situation. And that's the great thing about geology. All of us geologists and geoscientists, we're accustomed to dealing with something that's not an exact,
That's right.
I say,
Right.
hey, that's what makes it, keeps us hungry, keeps us looking, keeps us going out to the field. So,
Okay, thanks.
it's a good approach from that. There was another question?
Thank you.
You're welcome.
Troy, I have a question.
Yes.
What are these handheld Spectra guns that we have that we can point at drill chips and see minerals in there? I
Oh,
mean, I'm using one on and off right now that with a newfound vein system that has a different set of galena and gold and zinc and lead and silver minerals.
and you have a handheld scanner now?
Well, it's they've been around for several years.
XRF.
The
XRF.
XRFs, but
Oh.
they're getting better and better all the time.
Yeah. That's another thing. Technology is moving so fast.
Yeah.
The advancements are nuts. Just one little piece I'll share with you. Everybody in the room here is familiar with the water that's found the water that's on the moon.
Yes. In the shadow zones of the craters.
Do you know how we found out?
Somebody go for a swim?
Okay, it's so amazing. So what happened was, in order to, the hyperspectral tools, whatever that was around, you need to have a reflectance in order to get the data, right?
Yeah.
But if it's in the shadows, how do you get reflectance?
Aha.
So guess how they did it? These guys are amazing.
Laser beams.
No. Guess how they did it? So what was done was, well, if it's in the shadows, where else is there a source of electromagnetic radiation other than
Uranium.
the sun? Other than the sun.
Radioactivity.
From where?
Uranium in the monazite.
No. Remember, it has to come down. It has to come down into those shadow areas and then reflect back to the instrument. So what they did, they said, well, we need a place that's really dark.
Yeah.
So let's go to the other side of the moon where it's dark, right? And what they did was take the cosmic radiation, background radiation, the gamma radiation, and use the gamma ray spectrometer to receive the light, to receive the electromagnetics, right? And that's how they're able to identify water on the moon, by using the background radiation of the cosmos.
Wow.
Yeah. Okay, that's how powerful, how versatile all of this stuff can be. Okay, amazing sets of applications.
Troy,
Now-
you're about to run out of time, so.
That's okay. That's okay.
Turn the hourglass over, Troy.
I'm right. There can be a more heavier class. It could be a heavier class where we could, and I'd be willing. I'd have to get my the okay to use the software the way I would like, but I'd be willing to do a little workshop where we can download data and try to process a small thing. I'd be willing to do that.
That's a good idea.
So
Sure would be.
the last thing I'm working on with this, is the concept of phosphates. I'm a big fan of phosphates. And most recently, we also discovered that there are phosphates on the moon. And I'm in the process of using hyperspectral to identify those minerals. But the reason why we think this is important is because, of course, what do we use phosphate for here on Earth?
Fertilizer.
Yeah, fertilizer, agriculture. And now we know that with the adapting technologies of growing foodstuffs in contained environments, lab-grown meat, which when people think of lab-grown meat, they think it's something that's artificial. Do realize these are stem cells from animals, the fat from the animals. And this is probably, you could quote me, but I haven't seen anything that says it's not, but it's probably healthier than all the chemicals and stuff that we pump into animals today that we eat, right? So if we're able to utilize, once again, this is in the future, not tomorrow, but in the future, where we have facilities on the moon, and they realize these are not facilities that are on the surface of the moon. These are facilities that are probably going to be buried below the lunar regolith in caverns and things like that, because those have protection from the cosmic radiation, because that's what's going to be around you. So it's logical to be in an environment like that and only come out periodically, or you send your robots to do all of the work and you're just monitoring from inside. But it's definitely coming where there are going to be people there and they're going to need to eat. And we've made such advances utilizing the ISS for growing food in space. And with the applications with the DNA, making it grow better or in a certain environment, so it's not going to have to be that different, but we're going to still be able to make foodstuffs that will be healthy for us.
Wow.
Because it'll be natural. The only difference is that it's just grown. Okay.
Wow.
So there's lots to come.
New York steak on the moon.
there's lots to come. And I think we're going to see some really interesting things these next several years. There's a hyperspectral probe, a hyperspectral camera that's being sent to the Jovian system, because they want to try to look through the ice. Hyperspectral, these things do really well with ice. We're able to go miles through ice here on Earth through these type of instruments.
Wow.
So we're going to be able to probably be able to see through the ice going around some of those things.
You can look through the ice with the hyperspectral instruments.
With some of the tools that are used, not in particular the ones that we're using here, but there are some tools that they're able to look through the ice.
You're not talking about radar.
It's definitely a type of radar.
Yeah.
I'm not supposed to talk about. I'm not supposed to talk about.
You can also look through salt with radar.
Well, I mean, there's that moon that runs around Jupiter that's all just miles and miles of ice with liquid water underneath, hypothetically.
Yeah. Supposedly there's more. I may be wrong on this one, but I did read that there's a lot of water on the moon. There's more water on the moon than we ever expected.
Wow.
And it contends with the amount of water that could be that's on the Earth. It contends with that.
Yeah.
That's what they're saying. And of course, the Jovian moons, there's more water on the Jovian moons. Each one has more water than what's on Earth.
Oh yeah. Their entire surface is water. So,
Yes, it's ice, but it's several miles thick of ice, but it's 40. They've modeled. Okay, we haven't done it, but they have modeled. The astrobiologists have modeled what the moon, modeled, say the moon of Europa.
Yeah, Europa is the one.
Moon Europa, and Europa is some of their models have estimated that the water column is about 40 plus miles deep.
Wow. Underneath several miles of ice.
Yes.
Yeah.
So they're saying, who knows what could be, we don't know.
Oh, Troy, I've got a quick question.
Sure.
Has anyone done much remote sensing for petroleum, such as reduced zones, and then combining that with radiometric data and maybe even iodine and other data for oil and gas exploration using hyperspectral?
I'm sure they have.
Well,
I'm sure they have. I don't know about iodine, but I know that because I actually read some reports of oil production. They're using hyperspectral, but they're using it for the purposes of environmental.
Mm-hmm.
Right.
They're using it for surveillance. Okay, so there, I can't remember the name, but there's a company or an NGO called Open Sky or something like that. But they
Open
go out
Skies,
there- huh?
John Amos, we had him on talking to us in November or December.
Yeah, there's an NGO that basically gets as much satellite data as they can, and they look at what people are doing and they identify when there are problems and they report them. So yeah, there's a lot.
Good. Good.
I could see looking for source rocks with organic source rocks that would be useful in oil and gas exploration, because like the Eagle Ford has proxies of vanadium, maybe.
Yes, okay.
And what else? Somebody help me here. Is it molybdenum or manganese? Nickel, I think is one of the
Yeah,
proxies.
nickel is common.
Nickel, vanadium, nickel.
Yeah,
and
it's a breakdown of chlorophyll, so you will see it as in oil and gas source rocks.
No,
Yeah.
vanadium is common in the Jurassic salt wash formation.
Mhm.
Yeah, well, you see it in the Eagle Ford in the cuttings. I mean, if you're doing compositional analysis on wellbore cuttings, and of course, then you could take that to the outcrop and look
Yeah.
around for source rocks.
There's been an awful lot of work done on music.
Yeah, and
Looking for oil and gas anomalies, vegetation anomalies, soil color anomalies, and all sorts of things. But it's been very hard to come up with hard answers.
yeah, but let me say this. One of the people that I worked for, his name is Reggie Spiller. Some of you may know
Oh
him.
gosh, Reggie.
And Reggie Spiller I know he's done a lot of GIS work, geospatial work with oil and gas. He might be a great contact for who's doing what in the oil and gas field with geospatial with
And I have 3 publications on the Lisbon Valley field in Utah. So the same sort of thing. Yeah.
And folks, I do see that there's a couple of questions on the chat. Any recommended books or training materials? Man, these are tough. Is there any way I can get folks, please send me an email. That would definitely help. I'll post my email again right here.
Right. There's a question from Mike Norrid, which I can't read because it's got something over the top of it.
Well, someone asked if a recording will be available. Please advise members get a copy of the recording. Lunar hyperspectral images are meter scale and resolution. This is from Bryce C. Hoppy. Each meter includes all that anorthite and diopside and a half dozen other minerals with their respective spectra. Identifying distribution of each mineral from the combined spectra from the collective admixture. How? Oh, they missed that part. But it's a comparison with the reference spectra. And by taking the reference spectra, I tell the system, the software, to then highlight those pixels that match that spectra. So what happens is those spectra that are coming from the field are dominant in that reference spectra. That's what is possibly happening. So yes, you could have anorthite and diopside and other minerals in that field spectra, but the dominant reflectance reflects the reference spectra that we compare it to.
From Mike, for recordings, contact to Wendy Davidson or Kathy Duran, headquarters.
Yeah, I'm putting in the chat right now, John, about it. It'll be available on the YouTube channel and an email goes out. But if you subscribe to the AIPG YouTube channel, you'll know immediately when something is uploaded.
Oh,
Because there's several video or webinars. That's where all of them are available. you don't get certificates when you do that. You know, you need to attend this live webinar to get the certificate, but most of our webinars are recorded and are available on the AIPG YouTube channel.
Uh,
Thank you, Kawaja. Javed, thank you. He mentioned it's the absorption feature in the continuum removal. That's correct. The continuum removal.
I have a quick question for you, Mr. Troy. I'm working on the airborne hyperspectral with rock spectra and the field-based spectra. So my area is in Alaska, and where I am a graduate student right now. So one thing which I am facing in my research is that you are seeing from the airplane that it's completely rock, but when you are analyzing the spectral signature, it's just lichen, dead, fresh lichen, covering all over the place. And I have tried multiple approaches, and then I really can't figure out the way to separate the lichen spectra from the rock spectra, because
Oh.
because the spectra which I have in my area have a absorption feature between 2.2 to 2.4. The same region where we have different types of spectra like kaolinite, montmorillonite, and the other alteration mineral. So do you have any suggestion for this problem?
So let me understand. So you're saying that you have lichen on the rocks, so the rocks are covered?
Yeah, it's from the spectral signature. It looks like it's lichen, but if you are on the ground, it's almost rock. But from the spectral signature, it's showing that you have lichen all over the place. And I tried different approaches like restricted spectral range mapping, and I successfully mapped the iron minerals which have absorption in the 1 micrometer, but not the alteration minerals, which we are interested for platinum group element in the 2 to 2.5.
That's a tough problem.
And I talked with Mr. Coakley, and he looked at my data, and he was also kind of confused. You have just like in all over in your place, and I have got a very good high spatial resolution, which means that I have a data of 20 centimeter resolution, not 30
Ooh,
meter. So it's highly advanced data I have, but I'm facing this issue. So
First of all, I'd be happy to take a look and give you an
okay.
opinion. But at the same time, it sounds like that you should be able to have the ability to filter out the lichen. You should have the sort of like how we kind of filter out clouds from imagery data.
I have already done that.
You already did that?
Yeah, I'm using part software for auto rectification. Then I used AdCore software for all types of cloud removal, smoke, haze, that sort of stuff. It's completely clean data I have. So
that's a paper by itself.
That's the issue. I mean, I'm facing this since last 15 months, and it's one part of my master's thesis to defend your area of study without using any field data. You just have airborne spectral data, and you are confident that you have mapped the mineral correctly without using any rock or lab spectra.
Yeah.
So and that's a master's. That's a master's. And my PhD project is totally dependent on the result of this, because which is going to start in the August semester. So it's
gotta get boots on the ground, Kawaha.
This is John Berry speaking, and I've had experience of trying to do this kind of thing, not with lichen, but with other kinds of vegetation. And it's always been very frustrating, but you might want to look at the lichen signature itself and see if there are changes representing different assemblages of lichen overall from over and over. That's one approach. And I'm putting my email in the chat if you want to talk about this.
Okay, that would be great.
There was one other person. This is what was her name?
Michelle.
As far as books of training, there are plenty of books. I highly recommend, Dave, I highly recommend using Google Scholar. Find your topic, do a pull on Google Scholar, and you'll find citations, and read those citations. Read what made that person write that paper, and you'll find some awesome background, history, and scientific literature that will get you up to speed. The USGS they've updated their website. They did a fantastic job on their website. There's lots of projects, lots of coverages, as well as how-tos on their website now. Alexandria Price, I think the name was. I got
Yes,
your
that's
message.
correct. Thanks,
Yeah,
Troy. Appreciate it.
yeah, I got your message. Please don't hesitate. Send me an email. I'll be happy to discuss further.
Yeah.
That's
Troy.
perfectly fine.
Troy, I will be in touch with you to arrange a session on the process.
Okay.
Okay. And thanks for offering to do that. And I think we're a quarter of an hour over time, so we need to.
Okay. And I'm happy to, like I said, I'm happy to try to maybe build a workshop and go through the steps of processing, from ingesting, how to find the data, finding the data. That by itself is a trip. In my opinion, this is something that teams do, like data science. Teams. You have people that look for where, trying to isolate the data, obtain the data, and then you have to break the data down. There's really good tools out there, free tools for this. And then you have to get the data formatted in a certain way so that you can ingest it into your software program, and then run through the pipeline of steps of getting the data, having it prepared for spectral analysis. And then you have to set it up so that it repeats depending on the size of the survey. The survey is not very large, which most aren't, but sometimes you have to do something really big. It needs to go through an iteration, which can be time consumptive and actually expensive if you have to do it in the cloud. So, but I could try to put something small together like that. If there's also an interest regarding isotopes, isotopes is another one of my specialties, water vapor isotopes. I'd be happy to go through that one with folks as well, and a few others, if whatever interest that there might be, I'm happy to entertain.
Thank you, Troy. I know this was a fascinating presentation. I think it was made more fascinating by all the questions that were asked. So it was quite a give and take there. So wonderful. But Troy, will have you back. Okay.
Oh,
and
thank you so much.
And I want to thank Wendy and Kathy for staying with us for an extra quarter of an hour, for setting it all up.
Can I ask for one thing?
Yep.
If folks would like to turn on their cameras, I'd like to do a screen grab, because I've never had this many people show up, and I'm really pleased with that.
It's awesome.
Okay.
It's really great, Troy.
Oh, thank you.
It's a better attendance than we've had for a while, Troy. So good.
Well, I'm happy to do it again. Other topics. You count on me. I'm excited for this.
Great.
Remember, I'm also a college professor, so I can talk for 3 hours at a pop.
Okay.
That's great.
But yeah. And Jim,
Thanks,
was it Jim
Troy.
Levy that was asking the questions about hydrocarbon exploration?
Yes, I've done a lot of work with remote sensing, and of course, with reduction. And if you've read the AIPG memoirs, they've been you know a lot. I've worked a lot with that and done a lot of surveys. But I think the hyperspectral will be a wonderful addition, and then you could then combine it with radiometric. You can also combine it with geochemical.
Yep.
So I think it would be really fascinating, because I work in a lot of frontier areas, and I think it'd be a fantastic thing to see what hyperspectral tells us in combination and in coordination with these other techniques.
Well, I've done a lot of this kind of work, Jim, and I've put my email in the chat. So.
Thank you, sir.
Yeah. So, okay.
All right. Have a good evening, everyone. Good night.
Okay. Thanks very much, headquarters staff, and thanks very much to all the attendees.